I got one question, Alex.
Yeah.
What are the dates that we're going to have the midterm or the final exam take on?
That's a good question. I haven't thought about it yet, but I will think about it. And when I tell you this weekend that your midterm grades are done, I'll let you know when the final is going to be.
Okay, is it going to be like a week?
It,
I have some travel family
oh,
stuff.
yeah. Okay. So I'll probably do it over a week's interval, although my final exam will probably be a couple of hours of working on it. It will not be like your midterm turned out to be, I promise. I
Okay.
will learn from the midterm what to do and what not to do for the final. So, and just because it's a take home exam, that doesn't mean I expect you to work on it for 25, 26 hours. 35, 36 hours sounds more like it. So, no, I'm just kidding. I'm going to aim to do something that you can get done in a couple. Thanks, Madison. I think everybody online saw that, but anyway. Um, I'm sure I'm getting the finger from everyone who's just the name on the thing, but anyway. Okay, so yeah, but at any rate, so I'm going to aim for just a couple of hours working on it.
Okay.
Okay, so let's,
Alex,
yeah.
the lecture notes are last week Thursday for today.
Oh, hold on, let me fix that. That's just,
Your dates are a little messed up on the website too.
yeah, I believe my dates are screwed up. My dates are always screwed up. Yeah, it's because I have lecture 22 in there instead of lecture 23, which is what it is. And this is the 24th, isn't it? What date have I got screwed up?
No, I think you have like two of the lectures that you say the wrong dates in there. At least it doesn't match up with my notes.
Huh.
I think you just skip from the 10th to the 17th, and I think we did have class on the 15th. But that was,
No, you had a midterm.
that wasn't good.
Yeah, you had a midterm.
Weird.
But anyway, yeah, they should. Oh wait, do they appear now? Oh Jesus, I'm just being stupid right now. Can somebody check?
Yeah, I think I just opened them. It's 5 pages. Yeah.
So they're the current ones.
I mean, I think so. You
I
have
just don't. I don't know if I saved what I just had.
It said 22 before it.
It says 23 now. Yeah, it should say 23 now, right?
Yes.
Okay, good. Those are the notes for today.
Oh, lecture.
It's trying to think through this mask. It's just a little slower than usual. But anyway, all right, let's get going. So, oh man, this mask is falling off today. Okay. So we're going to start with I'm not going to quite present this in the order in which they did it in the book. I thought that was a little weird. We're going to start today with a complex generalization of Taylor's theorem. As you all are aware, Taylor's theorem leads us to the notion. Can I?
If you sit under the table, then.
Hold on, guys. I got to show you this. And I'm not even going to tell you what he's drinking. But anyway, sorry. Okay. All right. All right. So Taylor's theorem leads us, of course, to the Taylor expansion, the Taylor series expansion. So here's the complex generalization of it. If Fz is analytic everywhere inside a circle C, which is centered about Z naught, then in any closed region inside of this region C, WZ, which is going to satisfy exactly what you would expect for the Taylor series, oh boy. Undergoes uniformly convergence. So, no need to fret about this. We're certainly not going to prove it. Oh man, I'm going to have to abandon red. Oh, there's a tiny red marker. See, I was going to, hold on. Oh yes, we get to theorize this, but we're not going to prove it, so don't worry about it. At any rate, okay, so now this of course is not just, you can take a Taylor series and replace it with a complex variable z, and therefore you get a complex series, polynomial series. You've also got to have fz be analytic in the range where you're trying to do this. Okay? Here are a couple of examples which are going to take very familiar forms. E to the z, sum from n equals 0 to infinity of z to the n over n factorial. And this is going to hold for any z of magnitude less than infinity. 2 sine of z, sum from n equals 0 to infinity of minus 1 to the n, z to the 2n plus 1 over 2n plus 1 factorial. This is again for any z less than infinity. And then 3, 1 over 1 minus z is the sum from n equals 0 to infinity of z to the n for any z with magnitude less than 1. Okay? And these are all just Maclaurin type series, and so if you don't know, Maclaurin are just Taylor series that are centered around 0 instead of some arbitrary spot z naught. But nonetheless, these are all Taylor series, and they take exactly the same form that they take in real variables. So e to the x would be this with an x instead of z. It's that simple. Okay? We on board? Now let's look at something non-trivial. Consider e to the z, but instead of z, let's replace it with 1 over z. Okay? Then we have e to the 1 over z is equal to the sum from n equals 0 to infinity of 1 over n factorial z to the n. And this, of course, will work for any z of magnitude larger than 0. Okay, that's just the equivalent statement to a magnitude of z less than infinity. The magnitude of 1 over z is greater than 0. Max. Are you there? Max. I don't see Max on. Okay. Sam. Is Sam on? Yeah, Sam's on. Sam. I think you're on. Max. Or Sam. Sorry, I'm getting confused with names. Is this a Taylor series?
No.
No. Why?
All the powers of 0 are negative.
Yeah, all the powers are negative. Taylor series have positive powers. We know that. Okay? So that might lead you to question whether this is legit or not. It's certainly not a Taylor series. Okay? But it's going to turn out to play an important role, or it will be an important example of what we will find as a series expansion for complex functions. However, do pay attention, though, that this does appear, at least off the cuff, to be right, because these are all negative powers of z. So z equals 0 is obviously a singular point. Is z equals 0 a singular point of this? Yes, it is. Okay? So there is some agreement, but we'd like to figure out, where that agreement comes from. So we're going to have the complex version of the Taylor theorem, and this is due to Laurent. So Laurent's theorem says, let Wz the analytic, and this is going to get weird, in the region between C1 and C2, as shown, okay? So I'm going to take a point Z naught. I'm going to encircle it with a region, or with a circle C1, and then I'm also going to encircle it by a slightly larger circle C2. And then we want our function to be analytic, at least between these two circles. Then WZ is equal to the sum from n equals minus infinity to infinity of an z minus z naught to the n, where an is given by, and this is the most disappointing thing about a Laurent series, okay? When you want to do a Taylor series, if you want to find out the coefficients of the various terms in the Taylor series, you have to do what to the function?
Take the derivative.
Take the derivative. If I gave you a function and I said you've either got to take the derivative or integrate it, which one should you always safely pick?
Derivative, please.
Take the derivative, right? So if I say I'm about to disappoint you with the Laurent series, what are you going to have to do?
Multiply by 1.
Yes, you're going to have to multiply by 1. We're done. Let's go home. I'm just kidding. I'm just kidding. No. You're going to have to integrate. So in this case, the coefficients in the expansion are given by 1 over 2 pi I times the integral around a closed contour of the function over z prime minus z naught to the n plus 1 dz prime, where the contour C is just some closed contour, and maybe I'll put it in a different color just so that it stands out, and we'll make it green. It just needs to be a closed contour contained within the two, so that you're guaranteed that the function is analytic all along this contour C. Okay? Yes, okay, so the series converges uniformly in any closed region between C1 and C2. Okay? Now, shoot. Just a minute. Okay. So the first thing that we're going to do, I'll just do it. Okay, so the very first thing we're going to do is we're going to show how Taylor's theorem or Taylor's series come out of the Laurent series. The Laurent series are more general. Taylor is a special case. So let's see how Taylor follows from Laurent. Okay? So we want to take WZ analytic everywhere inside of the curve C. Okay, so we can set this up, but here's the important thing. We don't need this inner curve anymore. This inner curve is just a blockade which prevents us from being impacted by, for example, singular points sitting inside of here, places where the function is no longer analytic. Okay? But we're going to assume that WZ is analytic everywhere, so this inner curve is not really important anymore. Okay? Now, recall from the Cauchy integral formula that if this is the case, then WZ naught, where Z naught is any point within this curve C, WZ naught is 1 over 2 pi I times the integral around the closed contour C of WZ, Z minus Z naught dz. Okay? That is, if you want to know that, you should at least marginally understand this from your homework. But if you want to know the value of the function at the point Z naught, and everything's analytic inside of here, you can infer what the value of the function is at this point by integrating the function around this curve. However, your integrand is divided by the distance between each point on the curve and this point. Okay, so you're putting together these two pieces of information, the values of the function on the curve and the distance of the curve from the point, but that is enough information to give you the value of the function itself at the point Z naught. That's what the Cauchy integral formula does for us. Okay? Now, what we can do is we can imagine Z naught here is a continuous parameter. We can pick any Z naught in here that we want. So we might as well think of this as a function of Z naught instead of just W evaluated at a single point. Okay? But if you're imagining this as a function of Z naught, then you can certainly take derivatives with respect to Z naught. So let's do that. dW dZ naught. This might look hard, but Z naught only appears in one place. And we can interchange the integration and the differentiation. And so these derivatives turn out to be pretty simple. Okay? Now, just for simplicity, I'm going to move this 1 over n factorial factor under here. Okay? And now, what we can do is we can take, well, holy shit. The coefficients in the Laurent expansion are these derivatives. Coefficients, derivatives. So we can replace those coefficients with these. In which case what we get is that WZ can be uniformly convergently approximated by an z minus z naught to the n with an equaling 1 over n factorial times the nth derivative evaluated at z naught. Okay? That looks a hell of a lot like the Taylor series, except for one pretty nasty feature. Seth, what does this thing have that Taylor series don't have?
It goes from negative infinity to infinity.
Yeah, these only go from 0 to infinity. These go from negative infinity to infinity. It's a bit of a problem, no? Well, let's think about it for a minute. If I take the n equals 1 term, then I have to take the minus first derivative. What in the Flournoy does that mean?
The integral?
The
What is
integral.
what is the inverse? That's not the inverse, because then you're going to have -2, -3, -2. What's the w to the minus 963,427?
It's the inverse of the derivative is an integral.
How do you know that that's what -1 means? It's an inverse.
Because it's in the parenthesis, so it means that it's essentially the negative first derivative, which is the integral.
Well, if you do the derivative on that, you expect the function, right?
Okay. Okay. I'm going to explain this away. Because what I'm going to do is I'm going to replace this with 0.
Oh, you bastard. Why?
Because I'm about to argue that every n less than 0 gives you 0. So there's no point in including them.
Go for it.
Okay? Well, if I consider an n less than 0, I have 1 over z minus z naught to the n plus 1. If n is less than 0, and it's an integer, okay? So we can talk about n equals -1, in which case this becomes what?
1 over 1.
This becomes 1. What about n equals -2?
Over z. You get z minus z naught.
You get z minus z naught, etc., etc. Okay? Well, remember, wz is analytic. For n less than 0, so too is this function. The only points where this function is not analytic are the points where z equals z naught. But that's because it's a negative power. For n less than 0, the powers of this are all positive. So this is an analytic function for n less than 0, and w is an analytic function for n less than 0. Andrew?
Yes,
What can you tell me about the product of two analytic functions?
they're analytic.
What can you tell me about the integral around a closed contour of the vicinity of which these things are analytic?
Oh god.
You take an analytic function and you integrate it over a closed contour.
Oh, you get 0?
It's 0. So every single one of these, when n is less than 0, is 0, because you're just integrating around closed contours analytic functions. So we might as well lop off that weird negative integers part and just start it at n equals 0. Okay? Okay. All right. Okay, so, all right. So let me see. So I talk about how doing Laurent's expansion sucks because we have to do integrals instead of derivatives. Yeah, so the singularities are what's going to make the Laurent expansion interesting. And our next example is actually going to be doing a Laurent expansion in the presence of singularities. But bear in mind that this is again one of those regionally defined things. So I could have a singularity out here, but if I'm only interested in a Taylor series expansion of my analytic function over here, I can do that. Okay? All right. So now let's turn to an example We are going to have singularities, and we want to be able to laurent expand despite the singularities. So now consider the function wz equals z squared plus 3z plus 1 over z squared, with the point of interest being z naught equals 0. Okay? The singularity of this is obviously at z equals 0. Now, I am just going to walk you through this in detail. You're going to get a homework problem like this, so this is a point in the lecture where you might want to pay attention. Otherwise, you can just like, I'll figure that out in the homework and then go eat something. I don't know. But anyway, here we go. So the ANs are 1 over 2 pi times the integral around the closed contour surrounding this point of z squared plus 3z plus 1 over z squared times z to the n plus 1. Okay? All I've done is taken this and set z0 equal to 0 and then put in my function. All right? Now note, I don't have to pay very careful attention to the circle C1 and the circle C2 because this function only has a single singularity and it's at the point 0. So I can take this C1 to be as small as I want, and I can take C2 to be as large as I want. Okay? So here we go. First of all, note, for n less than or equal to -3, what does this become? Here, I'll simplify it for you.
Why do you have to wait until n is less than -3 to do that?
Huh?
Why don't you have to wait for n to be less than negative?
No. I'm saying I wrote it like this so that asking what happens when n is less than -3 will make sense. So if n is less than -3, Scott,
Hey,
if n is less than -3, what can you tell me about this function? This whole function?
I want to say it's 0, or we just don't care because
No.
of the previous argument.
Yes, but what is 0?
What is 0?
You said it's 0. So we got a friendly help.
Contour integral of an
Okay.
analytic function surrounded by the breakpoints that are 0.
Yes, if n is less than -3, then this is endowed with a positive power. Therefore, this is analytic, the product of two analytic functions is analytic, so we're integrating an analytic function on a closed contour so the integral is 0. So we don't have to worry about contributions with n less than -3. We on board? Okay, so that means if we're going to start this thing out, I mean, look, this is good news because in principle, where the hell do you start? Do you start at -infinity and then work your way up? Do you start at 0, work your way up to infinity, and then turn around and work your way down to -infinity? No. No, we want to find out the lowest value of n and then start there. So we'll start with n equals -2. Okay? So a equals a of -2, and I'll just erase this, we don't need it anymore. A of -2 is going to be 1 over 2 pi I, integral around the closed contour of z squared plus 3z plus 1 over z dz, which is 1 over 2 pi I, integral around a closed contour of z plus 3 plus 1 over z dz. Okay? Now, here's the story. Everybody hopefully figure out how I got from there to there, right? I'm going to do 2 of these 3 integrals, and you have to do the third. Done. Why? Because those are analytic functions. Z is an analytic function, so is the number 3. 1 over z is the only non-analytic function in here. It's the only one we actually have to integrate to get a non-zero value. That can't be that bad. I mean, 1 over z, if I take z to be e to the I theta, that is c is defined as a contour at unit radius that starts at 0 and goes to 2 pi. That's the contour we're going to integrate around. So if I make z equals e to the I theta, dz is I e to the I theta d theta. Well, holy shit. This becomes 1 over 2 pi I times the integral from 0 to 2 pi e to the minus I theta times e to the I theta times I times d theta. Holy crap. That's pretty straightforward. Right? So now let's do a to the minus 1, or a minus 1. Okay? Do you want to watch me or do you want to work it on your own? I want you to do this one on your own. Do a to the minus 1 on your own. Get you started. You should be well ahead of where I am. Jeez. It's been a long day. I'll do 2 of the integrals if you do the 3rd. Does that sound fair?
No, I think the easy two.
The second one's pretty easy. You just did it.
Yeah, how do you do the second one when you do the third for us?
0. You've already got the second one? Oh, dang. What's the second one give me? 3. Yeah, this one gives me 3. That's 1 over 2 pi I times the integral of 3 over z. Okay? So 1 over z squared is the only one I gotta do. Okay, fine. If I do the same thing that I did here, then this is going to be the integral from 0 to 2 pi of e to the minus I theta d theta.
You leave out the I.
Oh, yeah, I did.
I mean, that comes out to 0.
Yeah. Okay.
I'm not sure with all.
So a minus 1 is going to be 3.
All even powers.
Yes.
The denominator, right?
Yes.
And all the odd ones are just going to come out to 1.
Mm-hmm.
Exciting.
I know.
I like this intro.
Okay, so I'm gonna go ahead and let me see. We'll get rid of Taylor's theorem. Yeah. So in general, for an, well, let me just go ahead and tell you, a0 comes out to be 1. And then for an greater than 0, everything ends up being 0. Okay? All right? So, what we end up with is that WZ is the sum from n equals minus infinity to infinity, an z minus z naught to the n. And this comes out to be z to the minus 2 plus 3z to the minus 1 plus 1. It's just our 1, 3, 1 coefficients in front of the n equals minus 2, n equals minus 1, and 0 term. Of course, if this isn't z squared plus 3z plus 1 over z squared, I don't know what the hell is. So this was, of course, one of those trivial polynomial expansions where you're starting off with a polynomial. And unfortunately, to be quite honest, doing almost any other Laurent series is a pain in the butt. And it's largely because you have to do the integrals of the functions over z to the power. Okay? And that's a painful integral to do. You can obviously do it in a few cases, but not very often. I tried and tried and tried to find another less trivial case to give you as an example. I couldn't. However, you can learn some interesting things. So for example,
Alex, can I ask you a question before you continue?
yeah, go ahead.
So, is there a simplification that happens because when we looked at Taylor series, we looked about a disk. Can you do the same thing at infinity?
Can you do the same thing at infinity?
So, like, assume that the function is analytic not near the origin, but everywhere else.
That is a really interesting question. Yeah, that's really interesting, and it kind of grows out of the question you had on the homework where you were dealing with the branch points. Because it turns out if you have a single branch point in the space, then you automatically have another branch point at infinity, if you have no other branch point throughout the space. And that ensures you that any contour you draw, you can interpret as a contour around the inner smaller part of it or the outer larger part of it. And that's fine because, if you have a branch point at 0 and it changes your function by, e to the pi over 2, then the same thing happens if you encircle infinity because that one circle encircles both of them. Now, if you've got an analytic function which is only non-analytic at the origin, and you consider the integral around a contour surrounding the origin, you don't expect that integral to be 0. But if it is analytic everywhere else, you should be able to interpret that curve as a curve enveloping everything else over which the function is analytic, and therefore it should be, in that interpretation, it should be 0. Is this what you're asking?
Kind of, yeah.
Yeah, and I don't have a good resolution to that because I can't argue that a function which is non-analytic at a single point must also be non-analytic at infinity. If I could, then it would be fine. But I'd have to think about that. Yeah, I'd have to think about that. I don't have a quick answer for you. Yeah, I'll have to think about it. Other questions? Okay. All right, so what did I just, oh yeah, so let me very quickly, remember this? Okay, well, if we take this guy and we argue, well, this is actually a laurent expansion. That's where the negative powers of z are coming from. Okay? Now, this is the power of this. This we got just by taking the Taylor expansion and replacing z with 1 over z. We're confident this is correct. But what that means is that these are the answers to what are the integrals you're doing. Because you've already got the coefficients. So by sticking this into the Laurent series, you can conclude things like this. Okay? So this is just one of the interesting ways that people can get analytic results for integrals. All right? By not actually doing the integral itself, but having this framework where integrals are an important part of it, and then there are shortcuts to getting the answers to what you should expect, and then just by doing a term-by-term comparison, you can pull out results for certain integrals. Now, there is another idea about this whole analyticity thing, and it is the following. Suppose I am investigating a function at a point z0, okay? And sitting over here is a point alpha naught at which the function is not analytic. All right? Now, if I wanted to transform the function wz by a Taylor series, over what region can I do this? How about a circle that goes almost out, alpha naught? Okay? Make sense? Does that make sense? Okay, well, hold on. If I can get the Taylor series for every point in here, that means I can do the Taylor series about this point. Which, of course, is now going to give me a Taylor expression which goes out to, we'll stay green, here. Cool. Unless, of course, this is blocked by a second point where the function is no longer analytic. But that's okay, we can get away from this by picking a point here and going with a circle that big, and then picking a point here and going with a circle that big. So what you can do is you can take a function and you can extend it with a Taylor series throughout the entirety of the complex plane, excluding only the regions where the function is non-analytic. Okay? That's pretty amazing. This process is called the analytic continuation of a function. And it's really just starting with the function and its Taylor series representation in one region, and then just logically extending that. Okay?
This just works for discrete, like, problem points?
Yes.
Okay.
Yeah. Okay? You can't do this with real variables. Why not? What is it about analytic functions which is making this happen? What is a really big difference between analytic functions and functions of real variables? We talked about this last time.
Is it because you can go around the singular points because you're working in a two-dimensional space rather than a one-dimensional space?
I mean, that's an obvious story, but you could always do a two-dimensional, a function of two real variables. Analytic functions have a feature which is definitely not present for many real functions. Some real functions exhibit this, certainly, but not all of them, but all analytic functions do.
We're requiring them to have derivatives that exist, and they exist right next to the derivative where we're taking the derivative.
Exactly. Well, so you're using the definition of analyticity, that for an analytic function, to figure out whether it's analytic at a point, the derivative has to exist at that point, but it also has to exist in a neighborhood around that point. That's the difference between being differentiable and being analytic. Differentiable is just, can you take the derivative at a point? Analytic is, can you take the derivative at a point and a small neighborhood around it? Okay? That's the definition. But from the definition and various other massaging of analytic functions, we discovered something about all the derivatives. And I provided a counterexample for real functions last time.
Yeah, they all exist.
They all exist, exactly. All the derivatives of an analytic function exist. Do you remember this example I gave you last time for a real function which doesn't? So if we talk about f of x equals x times magnitude of x. Okay? Yeah, it kind of looks like that. The derivative looks like that. Second derivative looks like that. The hell's the derivative of that? It doesn't exist. Okay? And it's the fact that all of the derivatives exist that first of all makes the Taylor series a more effective thing, because you can always take it out to infinity. You don't hit a block. It's not like the third derivative doesn't exist. And this is part of the seed of why you can extend the definition of the function throughout the entirety of the plane, even only knowing it in one small region. Okay, I'm going to push on. I got one more thing, and then we're going to go. So I think I'm actually going to get done on time. But this is the nugget that I'm going to give you from the last section. Not the last section of the book, but the last section that I'm going to talk about. And there's actually nothing new in this whole section. It's just really an application of stuff. So I'm just going to very briefly go over it, and then we shall break and come back to green. It's functions. All right. So here we go. The integral of WZ around a closed path C containing a finite number n of singular points. Remember, singular points are by definition the points where a function is not analytic. Is equal to the sum of integrals around in circles, each containing a singular point. Okay, so let me draw the picture that underlies this, and you'll be like, oh yeah, of course, that's so stupid, I know that. All right? So consider a set of singular points and now let's consider a contour C which goes all the way around it. Okay? So again, we want to talk about some function wz dz, and the integral of this function would be 0 or non-zero?
Probably non-zero.
Yeah, we're taking it around this contour C, so this would be non-zero because it contains singular points. Okay? Now all I'm going to do is I'm going to transform this into a function whose integral is 0. So here's what we can do. I'm going to take, oh God. One of these tools won't work. They both suck. Anyway, okay, here we go. Instead of that, I'm going to follow, well, I'll just do it over here. So I'm going to come in, and then I'm going to jet down, and then I'm going to do a circle. I'm going to jet up, and then I'm going to come down, jet in, do a circle, jet out, come up, come down, come in, do a circle, jet back out, boom. Okay? Now, this is what we would call the contour C prime. It is not this contour. Okay? What's that equal to? So Z1, Z2, and Z3 are the only singular points in the neighborhood. There's no other singular points to worry about. So what would this integral be? This would be 0. Okay? We're assuming WZ is analytic everywhere except for the singular points. All right? Now, this integral is the contribution of many different parts, because I could think of like taking this straight segment as an integral, and then this piece as an integral, and then this straight segment, the circles as an, so we could just do a sum of a bunch of contributions to the main integral. However, if I take these two straight segments and I take them infinitesimally close together, think about it. The contour is going down on one and up on the other. So what do you think the integrals along these two contours are going to do if they get infinitesimally close together? They're going to cancel and give you 0, okay? So at the end of the day, what we have is that the integral around C prime of WZ dz, which is 0, is equal to the integral around C, which is what this outer part is going to become once these go to 0. That's going to become the closed integral around C prime. Well, it's going to become the closed integral around C, actually, because once you close it off, it's just going to become C1. 3 singularities. I could have done 2 and I'd have been done, okay? Obviously, then the integral around this entire contour is equal to the sum of the integrals around the small circles. Okay? You can actually write this as this equals, because in doing this, the direction of contour for the circles is clockwise, the direction for the outer one is counterclockwise. And if you define all of these to have the same orientation, so you take them all to be clockwise or all to be counterclockwise, that would put a negative in front of the negative that you get to move this to the other side of the equal sign, so it all comes out positive. So you can imagine that the direction of all of these is the same. And that explains where the minus went. Yes?
This kind of reminds me of Stokes' theorem. Is there any relation?
Yes.
Cool.
Very much so.
Neat.
All right, and let me very quickly well, actually, okay, so I was going to do an example, but I'm not going to keep you guys past 6:15. So I'm just going to make a statement, and then you can look at the example that I do in the notes. It's pretty straightforward, but I might integrate that into a homework question just to make sure that you look at the notes, okay? But here's the bottom line. Hold on, where is it? Where is it? There we go. Okay. So the notation that we actually use is the following. Why would we pick R? This is just a rewriting of this result in general. But why would we pick to symbolize it by R? Has anybody seen this before? Has anybody seen this before? R is called the residue. And now you should all be like, oh yeah, that's the residue. That's the residue theorem. Yeah, I remember that. Of course. No, okay. All right, that's fine. No, it's fine. But calculating the residues is pretty straightforward. You're of course going to use the Cauchy integral formula. Okay? Because this is what you're trying to evaluate. All right, it's pretty straightforward. I've got an example on the lecture notes. So you're welcome to look at that. Are there any questions before we disband? Okay, hopefully you all sent me your quiz. Again, I'm going to email you this weekend. I'm going to let you know about the final, and I'll be letting you know that your grades are entered into Canvas for the midterm. All right?
Do we have a quiz next week at any point, or no?
Yeah, you will.
Next Thursday?
Let me think. Yeah, we can have one next Thursday.
Okay.
Yeah, we'll have.
So next homework due next Thursday?
Yeah. Your next homework will be due next Thursday. Yeah. There you go. All right. Ciao.